In this lecture video, I'm going to give an overview, a very quick overview, of characteristic roots and characteristic vectors. Now, the reason we cover this material is because many of the procedures that we use in multivariate statistics have as part of their solutions characteristic roots and characteristic vectors. Now, characteristic roots and characteristic vectors are also known as eigenvalues and eigenvectors, respectively. Now we'll start off first with some definitions. So let cap sig be a p by p matrix. Suppose there exists a p by 1 non-zero vector A and a real number lambda such that this vector equation holds. Now let me just talk a little bit about both sides of this equation. On the left-hand side, we have the product of a p by p matrix and a p by 1 vector. And that product, the result of that product, is a p by 1 vector. So on the left-hand side, we have a p by 1 vector. On the right-hand side, we have the product of a scalar and a p by 1 vector. And the result of that calculation is, again, a p by 1 vector. So in order for this equality to make sense, we have to have the same kind of object on both sides of the equation, and we do. On each side of the equation, we have a p by 1 vector. And in order for the equality to hold, each corresponding element in those p by 1 vectors has got to be equal. So, if there exists a p by 1 non-zero vector A and a real number or scalar lambda, such that this equation holds, then lambda is called a characteristic root of the p by p matrix cap sig, and A is called a characteristic vector of cap sig corresponding to the characteristic root lambda. Now, let me just point something out here. You'll notice that the page number changed from 2 to 5. That's intentional. I've left out some details. I've intentionally left these details out because those details involve some of the mathematics underlying these concepts that we're talking about. And in subsequent slides, some of those details involve actually extracting characteristic roots and characteristic vectors from matrices. And that's not going to be that's not going to be our focus in this class. I'm not going to have you extracting characteristic roots and characteristic vectors, so you don't need to worry about that. Anytime we need characteristic roots and characteristic vectors, the software is going to calculate those things for us. So if you see gaps in the slide numbers, just rest assured that that is intentional, and I'm leaving it out intentionally because I don't want you to feel like you have to learn those kind of mathematical details, because that's not the purpose of this class. If this were a linear algebra or a matrix theory class, then we would probably focus on those details and you would be held responsible for them on tests and assignments. But that is not our focus, and so I don't want you to be distracted by that. Okay, now let's talk about some characteristics of square matrices, and again we'll give some definitions. So let cap sig be a p by p matrix. So it's a square matrix. The number of rows and the number of columns are the same. Now they're both equal to p. Now cap sig is said to be a positive definite matrix if this relationship holds for all non-zero vectors x. Okay, and so we're not going to go into detail on this because, again, we really don't need a whole lot of detail. But this is a quadratic form, and it's a product. So we have a p by 1 vector x, and so this is saying take the transpose of that vector. So the transpose of a p by 1 vector would be a 1 by p vector, and then multiply that against the p by p matrix cap sig, and then multiply that by the p by 1 vector x. And so the result would actually be, you can think of it as a scalar. Technically, it's a 1 by 1 matrix, but it's treated typically as a scalar. And so anyway, This is the definition of what it means for cap sig to be a positive definite matrix. Now, we also have positive semi-definite matrices. Cap sig is said to be a positive semi-definite matrix if this relationship, rather than being strict, is non-strict for all non-zero p by 1 vectors x, and it's equal to 0 for at least one of these non-zero p by 1 vectors x. And then finally, cap sig is said to be non-negative if it's either positive definite or positive semi-definite. So what we need to know and take away from this slide is that if a matrix, if a p by p matrix is positive definite, or if it's positive semi-definite, then it will be non-negative. And that's going to be important for us because as we start talking about covariance matrices, we'll see that that characteristic comes into play. Now, let cap sig be a p by p matrix. Again, on this slide, we're talking about characteristics of square matrices, and again, some more definitions. So let cap sig be a p by p matrix. Then the trace of the matrix, cap sig, which will be denoted this way in these notes, is defined to be the sum of the diagonal elements of cap sig. So if we denote the ij element of cap sig by sigma sub ij, the trace of cap sig is going to be is defined by this. It's given by this summation here. So remember that when we say the ij element of a matrix, we're talking about the element in the matrix in row I and column j of that matrix. Now you can see here that the subscripts on sigma are the same in this expression. And so what that is telling us is that we're looking at the elements in this matrix that they're in the same, they have the same row and column number. So in other words, sigma 1, 1, sigma 2, 2, sigma 3, 3, and so forth, down to sigma pp. And so those are the diagonal elements in that matrix. And so what that means is that we're adding up the diagonal elements, and that is what gives us the trace. Now, let's look at using characteristic vectors and characteristic roots to determine properties of symmetric matrices. So this is a theorem. This is an important result, and in a matrix theory class, this would be proven. So suppose that cap sig is a p by p symmetric matrix. All right, and it's got characteristic roots lambda 1, lambda 2, and so forth, up to lambda p, and that for each k going from 1 to p, let a sub k denote the length 1 characteristic vector of cap sig corresponding to the kth characteristic root. Then the following results hold. The first is that all of the characteristic roots of cap sig, all p of them, are real numbers. Right? None of them are imaginary numbers. None of them are complex numbers. All right? They're real numbers. Point 2. The characteristic vectors corresponding to different characteristic roots are orthogonal. Now what that means is that in a p-dimensional space, they are perpendicular. All right? Mathematically, what that means is that their inner product is going to be 0. All right, so for I not equal to j, okay, so what we're talking about here would be characteristic vectors corresponding to different characteristic roots. A prime, the transpose of ai times a sub j would be 0. So this is how we would compute the inner product of those two vectors. And anyway, so this is just the mathematical result or the definition of vectors being orthogonal. Okay, result 3. The trace of cap sig, which we defined a second ago, is actually equal to, in this particular situation, the sum of the characteristic roots. So let me go back a few slides. Okay, remember that by definition, the trace of cap sig is the sum of its diagonal entries. What we're saying here is that if cap sig is a p by p symmetric matrix with characteristic roots lambda 1 through lambda p, then not only is the trace of cap sig equal to the diagonal entries in that matrix, but that trace is also equal to the sum of its characteristic roots. Now, what's even more helpful is that the determinant of cap sig is equal to the product of its characteristic roots. Now, we're not going to go into detail about the definition of a determinant and how, in general, it's calculated, at least in terms of its by the definition. There are other ways to calculate determinants using some other formulas besides the definitional formula. But even those, typically all the different formulas for calculating determinants are very time-consuming and very complicated. But if we happen to be in this situation where we've got a p by p symmetric matrix, then the determinant of that matrix is equal to the product of its characteristic roots. Now, just a moment ago, we defined what it means for a matrix to be positive definite and what it means for a matrix to be positive semi-definite. All right, and the criteria seemed kind of complicated. It involves calculating the value of some quadratic forms and things like that. Those involve matrix multiplications and all that, and we don't really want to have to do that. But in this context, again, if we have a p by p symmetric matrix, then we have this really nice result. It says that the matrix cap sig is positive definite if and only if all of its characteristic roots are positive. So instead of having to calculate a fairly complicated quadratic form, all we have to do, if we have the appropriate software and can obtain the characteristic roots, is just to look and see whether or not all of the characteristic roots are positive. And if they're all positive, then that matrix is positive definite. Result 6, the matrix cap sig is positive semi-definite if and only if all of its characteristic roots are non-negative and at least one characteristic root is 0. So again, this becomes just a matter of inspecting the characteristic roots to see if they're all non-negative, and if so, if at least one of the characteristic roots is 0, then we can conclude, without having to do any other mathematics or calculations, we can conclude that the matrix cap sig is positive semi-definite. Okay, so let's look at some examples. So this is a very simple 2 by 2 matrix for cap sig, and so what we want to do here is answer several questions. First of all, we want to find lambda 1 and lambda 2, the characteristic roots of cap sig. And by the way, let me just point something out. Let me scroll back here to really the first slide. So where we were defining characteristic roots. When we have a p by p matrix, there are going to be p characteristic roots. All right, and when the matrix is symmetric, then we know those roots are all real numbers. Okay, so when the number of characteristic roots that a square matrix has is equal to a square symmetric matrix. That is equal to the dimension of the matrix. Okay, so since this is a 2 by 2 matrix and it's symmetric, then there are going to be 2 characteristic roots, and they will both be real numbers. So in problem 1 here, we want to find the characteristic roots. Now, I'm going to find those. I'm just going to give those to you. Again, our focus is not going to be extracting characteristic roots from matrices. Our focus is going to be how to use them. So I'm going to give you what these characteristic roots are, and then we'll go from there. Problem 2, find the general form of the characteristic vectors of cap sig corresponding to each of the characteristic roots lambda 1 and lambda 2. Well, I'm going to amend this a little bit. What I'm going to do is give you some let me see here. Let's see. Okay, we're going to skip probably 2 and 3 and jump down to 4. Find length 1 characteristic vectors of cap sig corresponding to lambda 1 and lambda 2. So again, if we were going to go into a lot more detail, we would show how to find these characteristic roots, and then we would also do some of this more general work, but we're going to be skipping steps 2 and 3 in the solutions. So step 4, find length 1 characteristic vectors of cap sig corresponding to lambda 1 and lambda 2. We're going to verify this property that the theorem told us was true, that the trace of the matrix is equal to the sum of its characteristic roots. We're also going to verify this property that said that the determinant of the matrix is equal to the product of the characteristic roots. And then we'll answer some questions about whether it's positive semi-definite, whether it's positive definite, whether it's positive semi-definite, and then finally, whether the matrix is non-negative. And then we'll answer the question, could this matrix be the covariance matrix of a multivariate normal distribution? If so, then find the following. We want to find the variance and standard deviation of x1, the variance and standard deviation of x2, and the correlation between x1 and x2. Okay, so for this matrix, and again, we're not going to do the mathematics to extract these characteristic roots. I'm just going to give them to you. But this 2 by 2 matrix has characteristic roots given by lambda 1 equal to 5 and lambda 2 equal to 3. Now, let me just point something out here. The convention that we're going to use in this class, and that's used in probably any statistics book where characteristic roots are used, is that we're always going to list the characteristic roots in descending order. So lambda 1 is going to be the largest characteristic root, lambda 2 will be the next largest, and so forth, down to lambda p, whatever p happens to be. Lambda p would be the smallest characteristic root. And so in this case, since p is equal to 2, lambda 2 is the smallest characteristic root. Okay, so these are the characteristic roots. Now, corresponding to the characteristic root lambda 1 equal to 5, there are 2 length 1 characteristic vectors of cap sig corresponding to that characteristic root. And those 2 by 1 length 1 characteristic vectors are A1, given by this 2 by 1 vector, and we could also use the negative of that. Okay? And then the length 1 characteristic vector corresponding to the second characteristic root, there are 2 of those. All right? And so we could use either one of these. Okay? And so A2 would be this 2 by 1 vector with entries negative 1 over the square root of 2 for the 1, 1 entry, and then 1 over the square root of positive 1 over the square root of 2 for the 2, 1 entry. So again, corresponding to each of these characteristic roots is a length 1 characteristic vector. We could use either A1 or negative A1. We could use either A2 or negative A2. Okay, now we want to verify that the trace of the matrix is equal to the sum of its characteristic roots. Now the trace, let me go back to and show the matrix. The trace is the sum of the diagonal entries. So the diagonal entries are the 4 here and that 4 as well. So those values are the diagonal entries. And you can see that the sum of the diagonal entries, which gives us the trace, is equal to 8. 4 plus 4, that's 8. Okay? Now notice also that the sum of the characteristic roots, 5 plus 3, is also 8. All right? So we see that in this example, this relationship holds. Next, we want to verify that the determinant of cap sig is equal to the product of the characteristic roots. Now, let me go back again to the matrix. For a 2 by 2 matrix, calculating the determinant is very easy, actually. What we do is we take the product of the diagonal entries and then subtract from that the product of the off-diagonal entries. So 4 times 4 minus 1 times 1. So 16 minus 1 is 15. So the determinant of this matrix is 15. Then looking at the product of the characteristic roots, we have lambda 1 times lambda 2 being equal to 5 times 3. That's also 15. So again, we see in this example that this relationship holds. Okay, not only is the trace equal to the sum of the characteristic roots, but the determinant is equal to the product of the characteristic roots. Now, is cap sig positive definite? Yes, it is. Since both characteristic roots are positive, cap sig is a positive definite matrix. Is cap sig a positive semi-definite matrix? No, it's not. Although both characteristic roots, lambda 1 and lambda 2, are in fact non-negative, neither is 0, and so cap sig is not a positive semi-definite matrix. Now, is cap sig non-negative? Yes, it is. Remember, in order to be non-negative, it's either got to be positive definite or positive semi-definite. If it's either one of those, then it's non-negative. Now, why is it important? Why are we interested in whether a P by P symmetric matrix is non-negative? Well, because that's going to allow us to answer this next question. Could cap sig be the covariance matrix of a multivariate normal distribution? And in particular, since P is equal to 2, could it be the covariance matrix of a bivariate normal distribution? Now, the answer is yes, and here's why. In order for cap sig, in order for a P by P symmetric matrix for it to be possible for that to be the covariance matrix of really any distribution, not just multivariate normal, but in order for a P by P symmetric matrix to be a valid covariance matrix, it has to be non-negative. It can be either positive semi-definite or positive definite, but it has to be non-negative. If a P by P, if a matrix is not square, then it cannot be a covariance matrix. If it's not symmetric, it cannot be a covariance matrix. And if it's not non-negative, it cannot be a covariance matrix. So again, and let me just say this, and I don't think I've got this written down in the notes anywhere. Typically, if we were in class, we would talk about this, and I would write it on the board or the overhead or something. But you need to write this down in your notes. So in order for a matrix to be a valid covariance matrix, it's got to be square, it's got to be symmetric, and it's got to be non-negative. Now, in this case, we know that the cap sig is square. It's a 2 by 2 matrix. It is symmetric, okay? And it's also now, based on our evaluation, based on looking at the characteristic roots, it's positive definite, therefore it is non-negative. And so cap sig could be the covariance matrix of a multivariate normal distribution. It's a valid covariance matrix. Okay, so then if we have if we let the 2 by 1 random vector x have a multivariate normal distribution with this covariance matrix, okay, then the variance of x1 would be 4. Its standard deviation would be the square root of that, which is 2. The variance of x2 would be 4 as well. The standard deviation of x2 would be 2 as well. And then the correlation between x1 and x2, well, remember that the correlation is the covariance divided by the square root of the product of the variances. Now let me go back here to the first slide for this example. So this right here, this is the variance of x1. This would be the variance of x2. This one right here, as well as this one, this is the covariance between x1 and x2. To get the correlation, we divide the covariance by the square root of the product of the variances. So the product of the variances would be 4 times 4. The square root of 4 times, which is 16. The square root of that would be 4. And so the correlation between x1 and x2 is 1 over 4. And that's what we get right here. All right, let's look at the next example, example 2. So let cap sig be a 2 by 2 matrix given by this matrix here. So we have the 1, 1 entry being 1, the 1, 2 entry being, the 2, 1 entry being 4, the 1-2 entry being 4 and the 2-2 entry being 1. So it looks an awful lot like the previous matrix. Let me go back to that real quick. Looks a lot like that one. We've just interchanged the diagonal entries and the off-diagonal entries. So again, we want to do the same thing. So I'm going to give you lambda 1 and lambda 2, the two characteristic roots of this matrix, and then we're going to answer the same questions. All right. Find the length 1 characteristic vectors of cap sig corresponding to these characteristic roots. Verify the trace is equal to the sum of the characteristic roots, that the determinant is equal to the product of the characteristic roots. Determine whether the matrix is positive definite, whether it's positive semi-definite, or if it's non-negative, and then answer the question, could it be the covariance matrix of a multivariate normal distribution? Okay, so for this matrix, lambda 1 is equal to 5 and lambda 2 is equal to negative 3. And then corresponding to lambda 1, the characteristic root lambda 1 equal to 5, we have this characteristic vector here, length 1 characteristic vector. We're not going to really pay too much attention right now to these. We're not going to do anything mathematically with them, but we'll use them later on as we look at some of the other multivariate methodologies. Okay, so then verify that the trace is equal to the sum of the covariance, the sum of the characteristic roots. So the trace of this matrix is 1 plus 1, those are the diagonal entries. And so 2, the sum of the characteristic roots, 5 plus a negative 3, that's 2 as well. So again, this relationship holds. Calculate the determinant and show that it's equal to the product of the characteristic roots. So if I go back here, remember that for a 2 by 2 matrix, the determinant is equal to the product of the diagonal entries minus the product of the off-diagonal entries. So 1 minus 16, that's negative 15, all right? And that is, in fact, the same as the product of the characteristic roots. So that relationship holds as well. Now, is cap sig positive definite? No, it's not. In this case, it's not because lambda 2 is negative 3, which is less than 0. So cap sig is not positive definite. Is cap sig positive semi-definite? No. Again, it's got cap sig has a negative characteristic root, and so it cannot be positive semi-definite. And I've got a typo there. In your notes, put semi-definite there. Is cap sig non-negative? No, it's not, because cap sig is not positive definite, and it's not positive semi-definite. Therefore, the matrix cap sig is not a non-negative matrix. Could cap sig be the covariance matrix of a multivariate normal distribution? No, it could not. Since cap sig is not a non-negative matrix, it fails to satisfy all 3 criteria required for a matrix to be a valid covariance matrix. Remember that those 3 criteria. Number 1, the matrix has to be square. Number 2, it's got to be symmetric. And number 3, it's got to be non-negative. And this matrix, while it is square, while it is symmetric, it is not non-negative. And so it's not a valid covariance matrix, and so therefore it could not be the covariance matrix of a multivariate normal distribution. Okay, moving on, let's look at another example. So again, we have a 2 by 2 matrix, cap sig. All right, and you'll notice here that we've got 1's on the diagonal again, and then we've got negative 2 for the off-diagonal entries. And so we can look here just very quickly. We can see here that the trace is going to be 2, and the determinant will be 1. 1 times 1, which is 1, minus 4, so a negative 3. All right, so let's just keep that in the back of our minds. We're going to answer the same exact set of questions. Now note here that the characteristic roots are lambda 1 equal to 3 and lambda 2 equal to negative 1. So you probably, you probably just thought, okay, this matrix is not a positive definite matrix, and it's not non-negative, it's not positive semi-definite either. Okay, and we know that now because it has a negative characteristic root. Okay, so we said that the trace of the matrix was 2. If we then calculate the sum of the characteristic roots, 3 plus a negative 1, that is 2 as well. So again, this property is holding. If we then calculate the determinant and look to see whether that determinant is equal to the product of the characteristic roots, well, we said that the determinant was equal to 3 when we were first looking at it. The product of the characteristic roots, 3 times a negative 1, that is also negative 3. And so again, this property that the theorem said would hold does hold, as it should. Is cap sig positive definite? No, it's not. Since it has a negative characteristic root, it cannot be a positive definite matrix. Is it positive semi-definite? No, it's not. Again, because it has a negative characteristic root, the matrix is not positive semi-definite. Is it non-negative? No, it's not, because it's neither positive definite nor positive semi-definite. So it is not a non-negative matrix. And then finally, could cap sig be the covariance matrix of a multivariate normal distribution? No, it could not be. It's not, because it's not non-negative, it is not a valid covariance matrix. So it could not be the covariance matrix for a multivariate normal distribution, or for any distribution, in fact. Okay, let's look at another example here. So we've got, again, a 2 by 2 matrix. We'll go through the same process, answer the same questions. While we're here looking at this, let's just note that the trace of this matrix is 2, and the determinant is 1 times 1, which is 1 minus 2 times 2, 4. So 1 minus 4, negative 3. Okay, so here the characteristic roots are lambda 1 equal to 3 and lambda 2 equal to negative 1. All right, we've seen those values before. Okay, verify that the trace of the matrix is equal to the sum of the characteristic roots. We said that the trace was 2. The sum of the characteristic roots, 3 plus a negative 1, is also 2. All right, so that relationship holds. We said that the determinant was equal to negative 3. The 1 minus 4, negative 3. The product of the characteristic roots, 3 times a negative 1, that's a negative 3. And so indeed, the determinant of this 2 by 2 matrix is equal to the product of its characteristic roots. Is cap sig positive definite? No. Again, since it has a negative characteristic root, it is not positive definite. Is it positive semi-definite? No. Because it has a negative characteristic root, it is not a positive semi-definite matrix. Is it non-negative? No, it's not, because again, it's neither positive definite nor positive semi-definite. So it's not a non-negative matrix. And because it's not a non-negative matrix, it's not a valid covariance matrix, and so it could never be the covariance matrix of any multivariate normal distribution. All right, now let's look at another example. Very quickly. We've got a 2 by 2 matrix here, and it's a little bit different, a little bit more interesting perhaps than the other matrices we've looked at. Now the trace of this matrix is 6, and the determinant is 4 times 2, which is 8, minus 1 times 1, so 8 minus 1, that's going to be 7. So let's just keep that in the back of our minds. All right, now the characteristic root, the lambda 1, is 3 plus the square root of 2. So that's kind of interesting, a little bit more complex, well, I don't want to use that word, but a little more involved than the others, other examples. Okay, and the second, the smallest characteristic root, lambda 2, is equal to 3 minus the square root of 2. Okay, now we want to verify that the trace of this matrix is equal to the sum of its characteristic roots. Okay, we said that the trace was equal to 6. The sum of the characteristic roots, 3 plus the square root of 2 and 3 minus the square root of 2, well, that's equal to 6 as well. So this relationship holds. We want to verify that the determinant of the matrix is equal to the product of the characteristic roots. Well, we said that the determinant was equal to 8 minus 1, or 7. If we calculate the product of the characteristic roots, we see that that is also equal to 7. Right? 9 times 2, or 7. I'm sorry, 9 minus 2. I said times. 9 minus 2, which is 7. Now, is this matrix positive definite? Yes, it is, because both characteristic roots are positive, and so cap sig is positive definite. Is cap sig positive semi-definite? No, it's not. While both characteristic roots are non-negative, neither one is 0, and so cap sig is not a positive semi-definite matrix. Is cap sig non-negative? Yes, it is. Since cap sig is positive definite, it is most certainly non-negative. Could cap sig be the covariance matrix of a multivariate normal distribution? Yes, it could. Because cap sig is square, because it's symmetric, and because it's a non-negative matrix, it is a valid covariance matrix. So then if we let x, the vector, the 2×1 vector x, with component random variables x1 and x2, have a multivariate normal distribution with this covariance matrix, then the variance of x1 would be 4, the variance of x2 would be 2, and the covariance of the correlation between x1 and x2 would be 1 over the square root of the variances, so 1 over the square root of 4 times 2, all right, and that would simplify to 1 over 2 times the square root of 2. Okay, so that is the end of this section of notes. I know that this is very, very fast, but we don't need to get into too many of the details, really many of the details at all, about characteristic roots and characteristic vectors. There's a lot more to these things mathematically, but that's not our interest, that's not our focus. We need to know how to use them for the purposes that we'll need them for in multivariate analysis. And what we've done in these examples is really a lot of what we'll need them for. Now, there are a few more things that we'll need to be able to do with characteristic vectors, but it's best to save that until we get into the particular context in which we'll need it. So I'm just going to wrap up this video, and we'll continue on with the next topic in the next lecture video.